Here I want to talk about logarithmic differentiation. This is a very special technique which can be used to find the derivative of a very convoluted looking expression. We will exploit the properties of logarithm. We'll simplify that complicated looking expression and then we'll find its derivative. I'll demonstrate the general steps that are supposed to be taken, and then I'll give you an example. So the general steps that you take are these. First, you start with a function. Let's say y is a function of x. So where y is equals to an f of x, where this f of x is a bit complicated. It is not evident straight enough. How would you take the derivative of that function? Using chain rule, it might be a bit difficult. Maybe some other technique won't work. So what you do is you take the logarithm on both sides, and before taking the logarithm on both sides, you ensure that they are positive. So both sides, or basically this right hand side, this needs to be a positive number, and which is often the case because you can find the logarithm only for positive numbers. So assuming that is the case, I can find I can say log of y is equals to log of f of x. Now the moment I've taken the log of this complicated looking expression using properties of logarithm, this can be further simplified. We'll see how this can be done using a specific example. But now if I were to take the derivative on both sides with respect to x, so if I were to take the derivative d by dx of this and d by dx of this, then you can see, first of all, on the left hand side you are taking the derivative of a log of y, where y is a function of x. So this actually is a this is an application of the chain rule, where you are taking the derivative of a composite function. This is a composite function of f, because straight away this is a function of y, but y is in turn a function of x. So if you are taking the derivative with respect to x, you need to apply the chain rule. And for the chain rule, just a refresher, what you do is you find the derivative of this function with respect to the variable that it has, that is y. So the derivative of log of y, the derivative of log y with respect to that variable y. So I'll take the derivative of that with respect to y, and then I multiply it with the derivative of y with x. This is actually our ultimate goal. This is what we want to find. And then on the right hand side, of course, I have the derivative of log of f of x, which we'll assume it is we are able to find that. It is easy to find because taking the log will simplify that expression using properties of logarithm, and then we'll be able to find the derivative of that expression with respect to x. And on the left hand side, we know what the derivative of log y is with respect to y. It's nothing but 1 by y. So this is kind of a standard derivative of a log is just 1 by that 1 by that variable, which is 1 by y. Remember, here we are taking the derivative with respect to y, so that's why it is a standard derivative. It's just 1 by y. This is of course dy by dx, and then the right hand side remains as is. It's d by dx of log of f of x. And if we want to solve for dy by dx, we just need to take care of this y. So if I multiply y to both sides, this will be cancelled. So what remains on the left hand side is dy by dx is equals to y into d by dx of log of f of x. And now if you want this completely in terms of y, you can completely in terms of x, I'm sorry. So you can this will be in terms of x, need not worry about that. And you can just now replace y with your f of x, because y was actually f of x to begin with. So you can replace this with f of x times d by dx of log of f of x. So if you look carefully, this will be completely in terms of x, and that is what actually the derivative of y is with respect to x. So yeah, a bit convoluted process, but it will become very clear when we take an example. So the example that I want to take here is, let's say y is the function x raised to x, and assume x to be a positive number. My domain is just for positive numbers, so it ensures that this expression is always positive. So I can take the log on both sides. I can say log y is equals to log of x raised to x. Now the reason I am doing this is because it is not evident how do I take the derivative of this expression, because the chain rule might not work. There's no other technique that we know of that will work. So we resort to logarithmic differentiation. We take the log on both sides. On the right hand side, you will observe something interesting happening, because we know from properties of logarithm that log of something to the power of x, then that power can be taken outside. So this expression is actually, it is nothing but this x exponent can be taken outside. This is properties of logarithm. And what I have here is nothing but a product of two functions. It's x and log x. So we'll see how we can take the derivative now on both sides. I'm sorry. So yeah, what we are left with is I'll take the derivative on both sides, d by dx of log y, which will be equal to d by dx of, now this is the product of two functions, which is x times log x. On the left hand side, just like we did in general, what will be left with is derivative of log y with respect to y, which is just 1 by y, and then derivative of y with respect to x. On the right hand side, we have a derivative of a product. So recall the rules of differentiation, which say that the derivative of the product, the way to find the derivative of a product is what you do is you start with the first function, multiply it with the derivative of the second function. Now the derivative of a log x, if you recall properly, it is 1 by x. So if I multiply this by 1 by x, this is what I get, and then you add the second function as is, that is log of x, multiplied by the derivative of the first function. Now the derivative of x is just 1. So if I look carefully, then this on the right hand side, x into 1 by x, this gives you just 1, and this is nothing but log x. So this is just 1 plus log x. So you observe that on the right hand side, the derivative, taking the derivative has become now easy. And on the left hand side, I am left with just 1 by y dy by dx. So if I were to shift this y over here, this would become a dy by dx is equals to y times this expression. This is 1 plus log x. So we are almost there. We just need to substitute what y was actually, and from our definition, y was actually x raised to x. So if I were to substitute it over here, this would become x raised to x times 1 plus log x. And we are done actually. This is an expression completely in terms of x, and that is what dy by dx is. So we have solved for the derivative of y with respect to x, and this is what the expression is. So yeah, we found the derivative of this expression, which was a bit difficult to find earlier, but now using logarithmic differentiation, we found its derivative to be this.